your zinc container on the outside with the zinc solution. Okay, so I'll have my zinc bar. And then inside of our porous cup here, we have hydrogen ions with our platinum bar. Remember the one electrode is platinum. We'll talk about why later. So you still have the zinc connected to the platinum, but now we only have one beaker for it. And what happens is, as the reaction happens and the electrons flow from the zinc into the hydrogen, the zinc is becoming positive ions. Now, as the positive charge builds up, what happens is the negatives that are over here, they migrate across the wall of the porous cup because it's porous. And so you can have the charged particles traveling right through the walls of the cup. And then the same thing for the hydrogen. As the hydrogen leaves and bubbles out, the positives from the zinc solution travel across the wall into the hydrogen solution to keep the charges balanced. So porous cups are an option, and U-tubes are an option, or even, like I say, a paper towel that's been soaked in an electrolyte solution will work just fine, too. For the battery lab, all this equipment is available to you. You don't have to bring in all of the glassware and equipment. We can offer that. You just have to know what substances you want to bring in. I'll talk more about the battery lab in a while. Okay, so here's just some terms that we're going to have to do. You don't have to keep redrawing the picture. The picture now is going to be the same through the rest of this. The electrons are leaving the zinc because zinc is willing to give up some electrons, and the hydrogen is very willing to accept electrons. So the electron flow has a certain amount of force. That force is determined by what the reaction's happening here and here. Some reactions produce a lot of force, pushing the electron through big time. Others, not so much. So the difference between the force that is sending the electrons out and the force that's pulling the electrons in, that makes up what we call the potential difference. Joseph, you got AP chemistry or AP physics? Did you have it last year?
Yeah, this year.
What is the unit of potential difference? Joseph, anybody else? Who are you pointing at? Maddie? Potential difference is what unit? What do you call the force that's that nature is pushing those electrons through with? The volt. Yes?
Yes.
Potential difference is another term for voltage. Yeah, yeah. Measured in volts. And everybody's heard of volts before. These reactions, like this reaction, if you had the right concentration of the zinc and the hydrochloric acid, or whatever acid, you might come up with 1 volt. So it's not like you're going to create an extreme danger with this kind of reaction. Now, we do have electricity that's available in the wall. If you stick a paper clip into the wall plug, you're going to be zapping yourself with 110 volts. That will get your attention. Yeah, the chemical reactions that we're going to be dealing with are on the order of 1, 2 volts. You know, it's not a big scare. All right, so anyway, another term for potential difference is this term right here, electromotive force. And so we can kind of dissect electro, meaning electrons. Motive means that they're moving. And force, so yeah, that's what electromotive force. It's measured in volts. So that's what we're going to be doing in this chapter, is we're going to be looking at what different reactions would be able to maximize voltage. Or even produce a voltage. So I know I gave you a definition of a volt up there. It's actually a derived unit. And it doesn't help us to understand what a volt is so much because a volt is a joule per coulomb. What the heck is a coulomb? What is a coulomb? I won't ask you. Coulomb is the unit for charge, electrical charge. You know, sometimes we'll talk about an electron having a -1 charge. That's actually a misnomer. An electron does not have a -1 charge. It has like something times 10 to the -19th coulomb. That's what its charge is. So yeah, we're going to be kind of toying around with the concept of the charge coulomb in this chapter. Coulomb is just a measure of electrical charge. When you have something that's that's charged moving around, we can measure how much energy it has pushing it around, that's a volt, or the rate at which the charge is moving, which is this thing right here, a measure of current. Current and voltage are not the same thing. Voltage measures how hard the electrons are being pushed from one side to the other. Current measures how many electrons are moving. But it's not really measuring electrons, it's measuring coulombs per second. It's like the flow of charge, coulombs per second. The unit of current, a coulomb per second, is also known as an ampere. And I know that you've heard of amps before. That's the unit of electric current. So that's something I really like about this chapter, is we can relate to it. We've heard these terms before. You've all heard of volts and amps or whatever. And so we can actually use them and do something productive with those terms, maybe get a little bit more of a feel. You won't get a full picture of volts and amps, like the origin of them we'll talk about, but a lot of the practical stuff is a physics context. So take physics. Just don't let them suck you into their weirdness. Joseph, you've done pretty well. Matt, you have too.
Why do you think John's not here when we're talking about this? He skipped it in for a reason.
That will be cut out of our video. All right. So, again, same picture. But we would call this setup an electrochemical cell. In fact, there are several of the homework exercises that are going to ask you to sketch a cell. I'll give you a chemical reaction, or the book will, and it'll say sketch the cell that would take advantage or use this chemical reaction. You'd sketch a cell like this, where the thing that's oxidizing is on one side. You'll have to show the direction of electron flow, like this is showing. You'll have to show where the reduction is happening. That's in a different container, like this. There's things that we haven't learned about yet, like the anode and the cathode that you'll have to label. Maybe you've heard those terms before. And you'll always have to come up with the cell potential. So the cell potential is going to be symbolized by a Greek letter. This is a Greek letter epsilon. It's like the Greek E. When I have to come up with that symbol, I just type a lowercase e, and then I highlight it and go to the Greek symbol font, and it gives me that. That's an epsilon. The book uses a slightly different E. It's a scripted E. I'll show it to you because I'll show you the table in the book. But yeah, what the voltage of that reaction is, how much the electrons are being pushed from the oxidation to the reduction, is determined by this. It's the oxidation potential. How much does zinc want to get rid of electrons? That's what that term measures. And how badly does hydrogen want to take electrons? That's the reduction potential. So you combine those two, and that's the overall potential of the reaction. And it's measured in volts. So the more volts you have, the more you could, the more energy there is to harness, we'll say. I thought we'd be done by now. I just have one little quick slide left, and that's this one. The standard reaction, or we'll call it a half reaction because it's got electrons in there. This is our standard half reaction. It's the reduction of hydrogen ions to hydrogen gas. You see that that has a reduction potential of 0. So there are some things that are better at reducing than hydrogen. Some things are worse at reducing. If it's worse, then it's going to have a negative reduction potential. So after the KSP table, in the end of the book, on page 825, is our list of reduction potentials. Remember, there's oxidation potential and then there's reduction potential. It turns out that there's only one table, though. And it turns out, I'm going to show it to you. switch